All right. I had hoped that I could have something put together. There's just no way in hell to kind of work off of. So we could either. I really want to go back because it looks like some of you guys are having some trouble with setting up limits of integration for one thing, right? Like back in 15.6. So we could look at problems directly out of the homework. We could look at trying out some non-homework problems and just seeing what happens. That's completely up to you guys. It's just like any other review day. It's a little bit up to you what we want to focus on. We could focus on
16.5 stuff.
16.5, sure. All right. Oh, let me do this. Okay. So 16.5. And I know I did this right at the very end very quickly, but it's really kind of a nuts and bolts section because it just lays the groundwork for these two things. It's sort of like when we first learned dot product and cross product. In my brain, I kept saying curl to myself because that's where I am. When we first learned those two, that section was really just a nuts and bolts. How do you work these processes? Because then the next thing you do after that is, once you learn curl and divergence, you can go back and rewrite some other earlier things in terms of them, and it just looks more, a word that's often used in mathematics, it looks more elegant. All right, so it looks more put together. Has anybody ever heard of Maxwell's equations? Yes. And let there be light. God, let there be Maxwell's equations. And it was so. Maxwell's equations are a beautiful example of uses of curl on electromagnetic fields and so forth. But if you haven't heard about it, that's okay. Don't worry. So this is, some of you guys, this might be the first time you've ever seen something written this way. It's an operator. So this can operate on a function. So it's got like these empty spots just waiting to be filled in. So we already talked about the gradient. It just puts the f pieces in there. Bam, bam, bam. So it operates on that function. You guys, how are we doing? Is that semi-decent? All right, I like it. This idea of operator is useful. It's a better way to write things other than function notation. Just let the thing attack something. Then we can do this. And we already talked about, you should have some way of doing cross product put together by now. Some of you guys might do it the way I do it, where I just write out the matrix and then write it next to itself and do the diagonal thing. Some of you guys just have it memorized. Right, but this is just purely, if they give me a function to work with, I just cross it with this and go to town. So, with that in mind, let's do something right out of 16.5. Yeah, okay. Let me make this a big old F. Bam. So let's say, given this, this is number 1, by the way, 16.5. Find the curl. And, in case you are somebody who prefers, do they give it to you all the way out? Yeah, here we go. Where are you? There you are. Now, if you're thinking about trying to memorize this, see how in the first part, this is going to be like the x piece of the answer, right? It's a cross product, so it's going to come out as a vector. We know that about cross product. Do you notice how nothing in here has anything to do with x? P is the x piece of the vector field. There's no dx. Same thing with the other one, same way, right? Do you notice how these are in alphabetical order? These are not. If you know anything about matrix multiplication or doing determinants, you know that this comes from the middle row, so it's going to be minus what it would normally be. So there are ways to memorize this that doesn't involve just straight up dr dy. Let me just repeat this to myself 18 million times, and then no, you can just kind of piece it together. You can memorize this; it's not impossible. Or you can just set the matrix up and do the diagonal stuff like we did before, right? But does everybody understand what I'm trying to say here? I know we didn't talk much about 16.5, but it actually I needed to do 16.5 to lay the groundwork in case you do get to a full treatment of Green's theorem or Stokes' theorem if you go into physics. Because it requires you to know what the curl is, what the divergence is, right? But 16.5 itself is not going to be a crazy difficult section because it's just brute force doing this. Brute force doing this. That's all it is. Right? And you guys are like, I don't think you know what that phrase "all it is" means, but I mean that section shouldn't be anything too crazy. I don't know if anybody's trying this out. So you can just plug and shove, really, right? Now, of course, to me, what's more interesting is the idea of what a curl is. And it has to do with, I got to talk about this a little bit, about how much rotation is evident in the vector field itself, right? The stronger the rotation, the stronger would be the larger the curl would come out to be. And that's why a curl of 0 makes sense that it's not rotational field at all. What if it was a conservative vector field? What would the curl be? 0. I love it. It would be 0. And that was why the other day I said, if it's conservative, what can you find related to this? If it's a conservative vector field, what can you find related to big ass F?
Anti-gradient.
I love it. Right? You can find the anti-gradient. The little ass f, that if you took the gradient of it, it would become this. So if it's conservative, then you end up with this, and we realize that these would point in the same direction. They're both the same thing. They would point in the same direction, so of course the curl would be 0. So if the curl of some vector field is 0, it's conservative, vice versa also. Right? It's not exactly a quick test. But that actually tells you now real quick, how would you quickly check to see if it was conservative? Well, if dr dy equals dq dz and dp dz equals dr dx and dq dx equals dp dy, then obviously it would come out to be 0. So that's kind of like that extension of dp dy equals dq dx. That's what we have to do for 3 dimensions now. We have to check 3 requirements. Maybe. All right, and you're just all brute force doing it. I chose number 1 so you can look in the back and see if the answer's right. Because I don't want to do it.
How do you set it up without not?
Okay. So you can either do this if you have it memorized or you have it staring you in the face. Or you could do ijk, d by dx, d by dy, d by dz, and then you put in there xy squared z, x squared y z, x squared y squared z. Some of you guys like to just do the determinant from this. Really good idea is to write it so that you can tell where things are. Right, does this look familiar? I mean, this is how you do cross products of two vectors. Right, and that's exactly what we're doing. That's a vector. Right, that's a vector. So I can do the cross product of those two vectors. So now you just, when you do this, it would be d this dx, d this dy, right? However you want to do. So you can either do the determinant of this, or you can write the whole thing again and then do those diagonal lines like we did before. Whatever makes the most sense to you. Hopefully at this point you've chosen something. You did enough cross products earlier this semester. You should have a way to do cross products by now. If you don't yet, hey, still get to choose. All the options are available. So in case you don't have the book and you're trying this out, what is it, 16.5? Ooh. It should come out to be 0. That's what the book says anyway. You never know. The book could have typos. But they claim it should come out to be 0. Let's check real quick. For this, what's dr dy? Which part of this is r? Let's identify. This is p. This is r. So what's dr dy?
X squared what?
2x squared yz, right? You guys, is that cool? The 2 comes down 2x squared yz. And what's dq dz?
X squared y.
Well, that sucks. No, it would be dq dz would be x squared y. Well, that doesn't look hopeful.
Is Q missing a square on the Z or something?
Let's see. No. Well, you never know. Like I said, they could get it wrong back there. X, y squared, z squared. X squared, y. Oh, this is missing a square there. Oh, Jeff, yay! Alright, screw it.
X squared.
But, I mean, the important thing there is the work involved with calculating this is actually not new work. The new thing up here is the idea of an operator like this. But it is a vector. There's a vector operator, really. So I can treat it as if it's a vector and then attack some given vector field with it. Yes, sorry. Did you have a question?
No, I was just going to say the y component of the cross product is 0, so maybe something that happened there.
Oh yeah, so each of these should be 0 independently. So now that I've got the right thing there, dq dz would be 2x squared yz. So these would cancel, and so forth. Because I was missing a square right there.
Oh, wait, did you write it?
Just now.
Oh.
Yay, I'm so helpful. All right, I'm sorry. You know, part of me is not interested in nuts and bolts shit. So, I mean, this is, the curl is defined to be this. Nothing new. It's a cross product. The only new thing is this. But what can I do with any vectors? I can take the cross product between two vectors. I can also take the dot product. And, of course, when I take the dot product between del and some vector field, that is called the...
Gradient.
No.
Alright.
The gradient is a weird little dude. All right, let me talk about this for a second. This is an operator. So what that means is it needs a functional input, and then it can attack it with all of its parts. So once I do gradient f, I'll put an f there, there, and there. So that by itself doesn't really act like you would expect a vector to do.
What's the derivative of a vector then?
So I mean, that's all this. This is a derivative components of a given function. But it's sort of related to scalar multiplication in a way of vectors. Yes, sir?
You can think of it like a blueprint. You just have to dump.
Yeah, but I'm trying to relate it to looking at them purely as vectors. If I do a constant times a vector, doesn't each of these components just pick up that constant?
Yeah.
So here, if I do that vector times f in a way, then each of these is going to pick up an f. It's not quite that because it operates on it, but that's the only relationship. These are more strictly exactly like what we're used to. They are two vectors, and the curl is just the cross product.
Okay.
The divergence is just the dot product. So if I wanted the divergence of this, I would just do d by dx of this plus d by dy of this plus d by dz of this. Right? When you do the dot product, that's how that works. Okay. Because what's I dot j? 0, because I and j are, by definition, perpendicular. And of course, dot product is going to be 0 when they're perpendicular. All right, maybe. Okay. So I know it sounds like I haven't talked about 16.5 much. I don't need to. It's all old stuff. The only new thing really is this. And then I'm like, okay, if that's a vector, would you guys agree with me that's a vector? Yeah, it's got an I, j, and k hat piece. Then I can do cross products with it. I can do dot products with it. Yes?
But when you use it as just a normal gradient function, the function you're taking the gradient of kind of has to be just one thing.
Exactly. That's why I said it's most closely related to like scalar multiplication. Yeah. But it's always this of this, not this times this. That's going to be the whole. That's the only real difference when we're doing these kind of problems. You can't multiply this times d by dx because d by dx really, in a sense, doesn't make any damn sense yet. D what dx, and so these get filled into the missing to those empty spots. All right. Let's do a smaller problem. Actually, I mean, this one's not too bad, but this comes out to be 0. That's not interesting. Let's do
the original.
Let's do this here. Blah, 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 blah. So, of course, what's interesting with this vector field?
There's a z but no z component.
Well, there's no what? Careful. No j component. No y component, right? So I would kind of tell myself that, right? Just to keep myself straight, put a little placeholder in there. So the work for this should be a little bit quicker. So if I want the curl of this, so again, and I would identify for myself, okay, that's P, that's Q, that's R. And then I can just go to town on it. It's a weird way to put it, but oh well, we'll survive. So the curl will be dr dy minus dq dz. And of course, anywhere I see a q here, it's going to be 0. I like it. So dr dy will be z e to the x. If you prefer to write it like that, it's totally fine. I mean, the I hat, j hat, and all that is just a different way to write the components of a vector, right? I kind of prefer this way, so fair enough. dp dz is going to be x, y, e to the z. dr dx is going to be y, z, e to the x. I mean, do you understand what I'm saying here? Are you guys kind of with me here? So either, and again, if you wanted to, you could fill this in with the new vector field, right? X, Y, E to the Z, blah, 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 and then do whatever the hell you do with it. Okay, cool. I honestly can't remember what I did as a student now. I hate that. I'm now far enough away from my student years that I'm like, I don't remember what the hell I did as a student with this. I can't remember if I memorized this. I have a feeling that I memorized this. But it's kind of gone now, so and then finally, this part's going to be 0, so then I get negative dp dy, so it's x e to the z, so minus x e to the z.
I think it'd be easier to memorize the formula for all cross products than just the same thing.
Yeah, it's the same thing. Yeah. In fact, I hate that this book makes this PQR. I kind of did that just to stay consistent with the textbook. But it'd be so much nicer to have something related to the X piece, the Y piece, the Z piece. I know they're in alphabetical order. But, still. Then it would make it a little easier to remember. Right? It's the Z with Y and Y with Z. Do you kind of see what I'm saying? Then it makes it a little easier to remember as you go across. But this is a part of what you need to do as a student. The teacher. You choose a teacher. Some of you guys didn't know me before you took this class, right? And you're like, okay, well, I don't know how this guy teaches. I don't know how he does things. And then you have a textbook that's chosen by the department. And how many textbooks are out there? Way too many. How many teachers are out there? A lot, right? So as a student, you have to find other resources. You have to figure out what makes the most sense to me. You have to maybe sometimes come up with your own way of looking at things. I like it. Somebody came in my office and they said something. I'm like, what is that? And they're like, oh, that's just the way I say. Was it you? That's just the way I say this. And I'm like, oh, I see what you mean. I don't think it was you, but it was their own. Was it Dave? Maybe it was Dave. I can't remember. But that's how you have to work math, is to make it your own. Okay. How about the divergence? What if I wanted to do the divergence? Dot product. Yeah. So now each component, I just attack it with the derivative of that with respect to that component. Does that make sense? The x component will be d by dx. Because it would be dot product, bam, bam, bam. So it would just be d by dx of this plus d by dy of 0, d by dz of this is a dot product. The divergence is a dot product, so the answer cannot be a vector. I like it. It's a very quick check you can make for yourself. Dot product answer better not be a vector. If you give me y and z values, this is a number like it's supposed to be. Curl, cross product, better be a freaking vector. I like it. So that's why I didn't really feel like I had to say too much about 16.5, because to be honest, it's not really loaded with a lot of new stuff. This is the only new thing. Yeah.
Is there something special about the gradient of the divergence?
Oh, what am I at here? So, what type of thing does let's kind of build up to that. What type of thing does a gradient need in here? Is this supposed to be a vector or what?
Plain old function.
Just plain old function. And when you take a divergence of a vector field, you end up with a plain old function. So you could totally take the gradient of the divergence. Now, what do you think this might mean? The gradient is going to be how related to, well, I don't want to say this.
Totally unrelated. There's no relevance between them.
No, come on. What do we know about the gradient? In fact, one of the homework problems was to draw out the contour map somehow. You could do it through Wolfram Alpha, and then draw on top of that the vector field that you generate when you do the gradient.
It points to the greatest rate of change.
But how is it related to the contour curves? It's going to have to be perpendicular everywhere. So we know that if I take the gradient of something, it should be perpendicular to the contour curves of that something, right? We know that it should point in the steepest, like Micah said, it should point in the steepest increase of that function. But when you start playing around with these things, one thing to be careful about is, am I allowed to do what I'm about to do? Could I take a curl of a divergence? No. Hell no, because that's not a vector. So, for example, I like it. But is there anything special about this? Is the question. Would that be somehow some special relationship with the original vector field? That's a good question. I mean, you guys barely have even started to think about divergence yet.
I mean, I think it depends on what the function represents, whether it's tangibly useful or not.
Well, remember that this has a relationship no matter what that guy is, right?
Yeah.
So this kind of inherits some of that, but is there something involved with the divergence that would play with that? I don't want to say. I might want to use that as a bonus thing or something. I can't remember. I don't think I assigned anything that's related to that, did I? I think they talk about that. No, I didn't. Shoot. They don't have that here. All right. But that's one example of trying to figure out. I don't know if you guys remember way back when we were doing like the volume of the parallelepiped. You remember that stuff? Oh shit. Right? And that dealt with cross products and dot products. So you start to wonder, is there some physical meaning if I start applying several of these processes on top of each other? It's not a bad thing to think about. So this is legal to do. And you can actually do it to that. Right?
Yeah, but whether it has physical meaning
Yeah.
or not is dependent upon the original function.
Again, not... Well, maybe in this case.
Yeah, because like, for example, after acceleration you got jerk. Then you have snap, crackle, and pop. But if it's a linear motion, then snap, crackle, and pop are completely meaningless. They have no physical meaning because you don't end up with anything.
But the fact that they're zero still tells you something.
I mean, I guess.
Yes. So, I mean, that's the kind of thing you could say, you can generalize. If it comes out to be zero, then it means that that thing is not present, or that thing doesn't affect it, or it doesn't have that quality. But you could still say, possibly, that there's something generally true about this. Anyway, I don't want to go too deep down there. How do you guys feel about 16.5? If you're able to do dot products and cross products, you should be good. Now, inherent in all this, you better know this. You've got to memorize this, but this is just beautiful, right? It's just the partials with each component, I, j, k. Pretty straightforward. Okay, cool. I like it. All right, maybe we'll make a bonus out of it. All right, so that's...
Is there 10 on this?
Oh, yeah, let's do that. Thank you. So on the practice test number 10, oh, real quick, I can't remember why I didn't, I think when I taught this last time, way back in, what was it, 2011, I think I told them if I didn't say which direction on the curves I was headed, it would be counterclockwise. So on a couple of these, like number 8 and number 10, I don't tell you which direction I want you to go. And that's kind of important. So I kind of I think on the answer key on number 8, I just went counterclockwise, if I remember correctly. Number 10, first off, can you just trace out the triangle that we're talking about? So 1, 1, 3, 1, 2, 2.
Direction you want, right? I mean, this isn't specified, but we have to take into account that if you go clockwise, it's negative, and then counterclockwise.
So I think what I did on, well, why don't you just look, Jeff. On number 8, I said, let's go counterclockwise, and then I said it would be negative if it was clockwise. So it covered my ass for both directions. So here, let's assume we're going counterclockwise. Let's say this is C1, C2, C3. Is everybody cool with where this came from, right? I mean, that's the triangle that I specified. So Green's theorem it needs for this to be conservative, but it would work. It says to get the line integral around something, you can actually just do the integral across the region itself of the derivatives of the part. So anyway, I'll let go of that. It's too bad we didn't have time for that. So what's true on C1? What's true on C1? What's y equal to, for example, on C1? Y equals 1. And x starts at 1 and goes to 3. So, I mean, if I let t go from 0 to 1, how could I define x, or do I want t to go from 0 to 1? So x can't be t if I wanted to do that. You could say x is t if t goes from 1 to 3. Sure. I like it. So David said, no, Jeff, screw that. Yes, sir?
Just do the parametric line equation, the 1 minus t.
Of course, definitely.
Okay.
Yes. So you can do r of t equals 1 minus t